Hi, I'm Ben-Yaakov. This presentation is entitled Explaining Interleaved Multiphase PWM Converters by LTspice Simulation. Now we see in many application notes and some other write-ups plots like this for the ripple of a multiphase converter. This is for a buck converter. This is from TI application notes. We see here the ripple at the input side and then the ripple at the output side. It is normalized, although it's normalized, I see here that the units are amps, which does make sense, of course. If it is normalized, then it is dimensionless. But that's not the only problem. The question is, how am I going to use this in order to actually estimate the ripple in a particular case? Here I see this is normalized. This is one phase, 2, 3, and 4 phases of the multiphase converter. And the question is, what is this normalization refer to? So what does it mean, 0.5? And then I have here a normalized at the output. This is kind of very strange, going up to 1. What is this 1 meaning? So there are many questions here. You probably have to read very carefully the write-up to understand what's going on, and hopefully you'll understand it. And then there are some other plots that you can get here from another publication from Design Lines. This is very strange. It's non-symmetrical. You would assume that it will be symmetrical between the low duty cycle and the high duty cycle, but it's not. Probably there is a reason for it. Anyhow, there are many questions here. At least I'm confused. So I've set up to look at these questions as well as some other fundamental questions. Now, if you sweep the duty cycle, okay, then there are questions, what are the conditions? You can have it under constant output voltage, that is, keep the output voltage constant and still sweep the duty cycle, or constant input voltage, sweep the duty cycle, in this case the output will change, or a constant power, or a constant current. So the question is, how can we get information for all these cases? Now, usually we are interested in the case of, say, constant power, and then it will be a constant voltage too, with a given resistor representing the nominal load. So in this presentation, I'm going first of all to look at what are the factors which are affecting the input and output ripple. And then I'm going to set up an LTspice simulation for ripple examination. And then I'm going to see how to normalize the simulation results out of these models. And then, of course, we're going to run a number of simulation examples, and all this by LTspice. So let me start off with this basic cell or module, you might say, of a half bridge. Now we can look at it as a buck. Here's the input and here's the output, or as a boost. Here's the input and here's the output. Waveform should be probably the same, and they are the same. Now, the definition of what is T on and T off is different. In the case of a buck, we call this T on when the upper transistor is conducting, and when the lower is conducting, we call it T off. And it's the other way around with the boost. T on is here when the inductor is charging, and T off is here. So, aside from the definition of the duty cycle, and the duty cycle of a buck D on is actually D off of the boost, then everything else should be the same. So as far as the waveforms and ripples, etc., I can treat it as one unit. So here is a first run of simulation, and what I'm showing here is actually a buck with a diode, just to simplify. As I've said, since buck and boost are the same, I can just run the buck case. And here are the diodes, here are the transistor, and they are driven in a shifted way. That is, the pulses are shifted. Here, this is the shift here, period, 3, 4. And then we have 4 inductors, which are all connected to, in the case of the buck, this will be the output. I'm calling this V1, and this is V2. These two sources are put just as a sensor for current, the total current here and total current here. So this is the very basic simulation setup for a multi-phase converter. And then I am running in parallel the case of a single inductor. In this case, I am running all these transistors together. Okay, so it's like they are in parallel. It's one big transistor, you might say. And all these inductors are together, so it's like one inductor with an inductance which is 1/4 of the basic inductor of each one of these separate inductors, and everything else is the same. So here is a result of a basic run. We see here the single inductor case very nicely, the inductor current, triangular waveform. The green is the drive. It's about 0.85 duty cycle. Here we see the drive for the multi-phase cases. You see it's one drive starting here, the other one starting here, this one here, and this one here. So they are phase shifted by 1/4, 0.25 of a duty cycle. And then we have the currents of the inductors very nicely interleaved. And this is why they are, of course, canceling partially each other, and therefore you get a total ripple which is lower. And in this case, they are the same height. This is because it's simulation, everything is the same. In the practical case, probably you'd like to have a sensing of the current and then have some mechanism control for current sharing. But here, with the simulation, you really don't have to do that. And here is the total current at the two ports, V1 and V2. V1 is like the input to the buck. This would be the single case, single inductor. You see that there is 0, and when the transistor is conducting, you see the inductor current, as a matter of fact, charging. And this is now for the multi-phase. You see the cancellation or partial cancellation between the inductors. And this is for the V2 side, the output of the buck. Again, this is the single case, single inductor case, large ripple. And here we see the partial cancellation very nicely, quite a bit of a attenuation. So let me go to the basics here. And I'm looking at this cell here, or this module, and I'm now considering the buck case. Current is going from here to here. And in this case, during the on, this is the on, we have a charging of the inductor, and the voltage imposed on it is V1 minus V2, and the slope is divided by L, times T on is the ripple peak to peak. This is this ripple here. Now I'm replacing V2 by D on times V1 for a buck. I'm talking about continuous current mode. And then also, instead of T on, I'm putting D on over the frequency, or D on times the period. That's what it is. And I'm getting this classical equation, which says that the peak-to-peak ripple is V1, this is voltage here, D on, D off over L, and the switching frequency. Now, this equation, or this expression, has a maximum when D on is equal to D off, 0.5. So the product is 0.25. This is the maximum point of this function. And now I'm moving to the boost case. Now the current now goes the other direction, so I call it negative, as referred to the buck case. This is why I've plotted it this way. Again, during the time that this transistor is on, which is the off time of the boost, okay, at the on time of the buck, I have the same slope, the same differences, and then again, when replacing V2 with the proper function, I get this exactly same equation, which should be, because as I've said, the waveforms are exactly the same, and the ripple is the same. So this will be for the boost. Now, I'm looking at this equation, and I see that in order to normalize it, I have to take out all the numbers for the specific case, which is the voltage, the inductor, and the frequency. So if I divide this by this factor here, V1, L, and switching frequency, I'll get a normalized value. So if I run a simulation and I get some ripple and I divide the result by this factor, I'll get the normalized curve or normalized information. And then if I need it for another case, then I'll get this normalized information or curves or plots and multiply it by the normalization factor for this particular case that I am now interested in to get the actual peak-to-peak or the RMS. It's the same thing. Okay, so this is the idea of normalization to the specific. So this is the idea of the normalization being independent on the particular parameters of the circuit. And now I'm moving to the V1 side, the input in the case of buck. The pulses here now are when the transistor is on. So you see here these pulses. For the boost, it'll be like a reverse, negative, but it's the same thing, of course. And then, in this case, I understand that the normalization should be to the average inductor current. So by dividing this by the average inductor current, I'll get a number or the information independent on the case that I'm examining or simulating. So these are the idea of normalizing such that the particular parameter of the circuit that you are getting the plots or getting the information will be taken out. So to get a normalized ripple, you have to do the following. You have first to run the simulation, and then for the V1 side extract the ripple, and then divide this ripple by the average current. So this will give you the ripple in a dimensional form. And then for the V2 side, you again extract the ripple and then divide it by this normalizing factor, and again you'll get a normalized curve or information. So let's see now how we carry out this simulation and normalization. So first of all, I have this simulation schematics, which I've shown earlier. And now let's go into some details. I'm defining parameters. D-on is a parameter that I'm going to sweep by this step command. And then the inductance and the resistance of the inductors is also a parameter. And then I have the 100 kilohertz frequency, and then defining T-on as D-on. This is D-on parameter divided by the frequency, which is 1 over frequency is of course the period, which is also defined here. So all these are required for the definition of the drive to the transistors, okay? This is now a transient analysis, and this is the range of the time, up to 3 milliseconds, starting to collect data at 2.9 milliseconds. So this is the range here, although I'll be running it at different ranges later on. So in the conventional transient analysis, you're getting information as a function of time. Well, that's not what we want. We want information as a function of D-on. So what we want actually is to run this for various duty cycle, for a range of duty cycle, for each one to extract information like, say, the peak-to-peak ripple, and then to present it in this form as a function of the duty cycle. So it's a different way of presenting the data rather than a collection of runs, sort of to summarize it. In PSpice, it is called performance analysis, okay? In LTspice, unfortunately, it's not simple, so let me show how we do it. The first thing to do is to do the extraction of the information of the data. So I'm showing first of all the V2 side. This is the output of the buck case. I'm going to run this simulation, the first one, under constant current condition. For constant current condition, since I'm sweeping the duty cycle, as I'm sweeping the duty cycle for a fixed input voltage, the output voltage will change. So in order to correct it to the same current, I am increasing the resistance proportional to the duty cycle. So therefore I'll get here a constant current independent of the duty cycle. So this is the first stage. Now for this particular run I have L6 microhenry, frequency of 100 kilohertz, and V1 is 60 volt fixed. So the normalization factor here, V1L times frequency, is 100. Now we go to the LTspice way of getting the information. There is this directive of measure, okay, which is associated with the step function. I am defining a parameters that I'm extracting. This is the syntax of LTspice. This is an operator. Find the maximum of IV3. IV3 is the current of V3. This is the current here, okay? So I'm looking now at the maximum value of this current, which is the sum of all these currents of the individual inductor. These are the individual inductor, and this is the red one is what I see here. And in this case, I'm looking at the maximum. I'm not going to use it. This is just for demonstration. Now, what I'm going to use is the average here, okay? Now, the average here again is a measure. I'm defining this as AV3 because it's V3, and this is the operator. So take the average of IV3. This is IV3, the IV3 coming here. Next, find the peak-to-peak. I'm defining it as peak-to-peak 3. Find the peak-to-peak of the difference between IV3 and the average. Average is here. I'm taking the difference. So this is actually the peak-to-peak curve, and I'm asking for a number that is the numerical value of this peak-to-peak, okay? This number, it's one number here for each run, for each duty cycle. And then the same thing goes for the RMS. Find the RMS of this difference, and this will be one number per run per duty cycle. And then for the normalization, I am looking at the results. This is the peak-to-peak, and this is the RMS, and taking these and dividing by 100, I'm now looking at the maximum of this curve. This is a sort of a line, so the maximum is the line itself, because this is a number, and this is a number. For each duty cycle, it's a different number, of course. So this is, the max is just this line, and I'm defining it this way, and this is really the normalized RMS. So this is for the V2 side. Now for the V1 side, everything is the same, the average, peak-to-peak, etc., except that the normalization now is the current, which is 144 amp, so I'm dividing it by 144. So these directives are actually getting the information I need for building the plots as a function of the duty cycle. So let me now demonstrate how to get the plots that we are interested in. So we've set up the simulation schematics with all the directive for the measure, step, everything as I've shown earlier. So the first thing to do is, of course, to run it by clicking here this run button, and here it is. So it started to run, and I can see how the simulation is advancing. You see here at the bottom, you see this is now run 4 of, here it is, 4 of 17. It shows when I'm here on this window. So I have now to wait until it'll finish. Okay, now that it's finished, I'm going to view here and getting to Spice error log for some reason. And then I'm clicking the right side and then clicking plot the step measure data. And now I'm getting a new window. This is now in terms of the swept duty cycle. Okay, the step duty cycle, the range that I have specified. I've specified from 0.1 to 0.9 duty cycle. Now with the right click, I get here add traces, and now I'm getting here all the parameters that I've defined. Okay, the peak to peak, the RMS, the normalize, etc. So let's have a look at a couple of these. For example, the RMS, okay, and this is for the inductor side, and this is for the switch side. This is V1 and V2, actually V2 and V1, and is okay, and here it is, okay. So I can change actually the color, so it'll be more friendly here. Say it's red. So now I got the information in terms of the duty cycle that was swept and the parameter that I have defined by the measure directive. So here is an example of one of the results, showing now a number of curves. This is for the, again, constant current case. This is for the single inductor, and this is for the multi-phase. I'm showing here only the RMS, just not to cloud it too much, not to have too many curves here. And I see here the V1 side is the RMS of the V1 side, RMS of the V2 side. This is for the single inductor. And here for the multi-phase, I see it very nicely. This is the V1 side, like the input of the buck or output of the boost. And here I see here the output side of the buck. I see here very nicely the 0. I have 4 inductors, so I have 4 portions here, 0.25 duty cycle apart. And this is for the full run with the numbers that I have for the input voltage, the current, the load, etc. And so these are the actual numbers, so these will be like in amps here, okay, for this particular case. So here is the normalized case. I'm now plotting the normalized parameters as I've defined them. And this is for the single inductor. Again, this is the multi-phase. And here I have for the V2 side of the single inductor, and the estimated value here is 75 milliamps. This is in milliamps. And let's have a sanity check here just to see if we get the correct result. So we have 75 milliamps. This is RMS. I'm just showing the RMS. To get the peak to peak, you have to multiply it by 2 first of all, and then square root of 3, because this is a triangular waveform. When we do this, we get 259 milliamp, and the theoretical value is 250 milliamp, which is very, very close. So we see that we are okay, and apparently we didn't do any error in the setting up of this simulation. Now I'm doing this normalization in a different way, dividing the multi-phase result by the single inductor result. Okay, that is, how much is the multi-phase case smaller or larger than the single inductor case. So this is probably what we see in the reference design, say, of TI. You see this increase here. This is because the single inductor is going down here, and when you divide it, you'll get this going up. Now the point is that this is really not important. What is important is the absolute value of the ripple. I don't care if it is larger or smaller than something. What is important to me is what is the ripple. You will get it here, in this case, in the actual value that we run the simulation, or you can get it in a normalized way and translate it to whatever case you are interested in. So this is this type of normalization that is different from what I was talking about. Now I have another example of a constant power case. By constant power, I mean that the output voltage is constant and the load is constant. This is actually what is usually of interest, because usually we like to keep the output voltage constant, and for the nominal value you like to keep the load or the resistance, which is representing the load, to be constant. Now, to run it in a constant power mode, since we are changing the duty cycle and I want to keep the output constant, then I have to change the input for each duty cycle, such that V2 is V1, this is here, times the duty cycle, okay? So if I make the V1 10 over the duty cycle, I'll get V2 to be constant at 10 volt, and this is what I'm doing here, okay? Here is the definition of this voltage source. And here is the result. I'm showing here again this normalization of the multiphase over the single inductor case. I see here two different features. First of all, I see this is not the same height, and also this is kind of very strange. Now, I don't know whether there is a simulation problem here or whether this is real, so I didn't go into it, and I'm going just to chop it out by zooming into the portion which looks more regular, and I really don't know what is really happening here. It has to be looked in very carefully. So let's leave it aside and then concentrate on the main picture here. So what we see here is that this now is changing. Why is it changing? Because the constant power means that the, say, current, the chopping at the input is different, okay, in the back-on case. Because as the voltage goes up, then obviously things are changing and you see different pulses at the input. So therefore, you see this difference here, but again, we are interested in the actual ripple, and this doesn't change much. Here, however, for the V2, for the output, I see some change here, okay? And so there is some difference because of the way the duty cycle is operational, but the main point here is that you have all the information here, and you can of course obtain whatever you need for your design. So this brings me to the end of this presentation. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.